Today we're going to focus on the additional topics in mathematics, class 7. We're going to begin with perimeter, area, and volume. And as I said at the beginning of geometry, lengths, lengths squared, and lengths cubed. Let's jump right into it. So I'm not going to spend a lot of time going into the basic formulas for the basic shapes of areas, perimeters. I would expect you'll know that on your own. For example, the area of a rectangle is length times width. I would expect you'll know that one. The perimeter is 2 times the length plus 2 times the width. Square is not shown, but the area is s squared, where s is the side length. The perimeter is 4s. I expect you know these things mostly. I'm going to focus on some of the nuances that you got to be careful of and look at some other more interesting things to add to this list. So a parallelogram. Notice a parallelogram very much like a rectangle, but angled sides A there. Do not try to do length times width or A times B. That would be bad. That would get a frowny face because you would not be correct. The length, or the base here, B, has to be multiplied by the perpendicular height. So that would be the correct way to calculate the area of a parallelogram. Triangles. We know a triangle, the area is 1/2 the base times height. It's essentially, if you think about it, a triangle is really just 1/2 a rectangle. So it's 1/2 the base times height, or length times width. Now, be careful. The height on the triangle, again, has to be perpendicular to the base in order for this formula to work. Trapezoid. Trapezoid's a little more interesting. It's a base on top and a base on bottom. We call those horizontal bases B1, B2. If we take the average of them, we effectively get the length of a rectangle, and a trapezoid, mathematically speaking, becomes a rectangle, because then we just multiply by the height, again, the perpendicular height, to get the areas. Circles, hopefully everybody knows pi r squared is the area of a circle, and 2 pi r, or pi d, if we're talking d for diameter, is the circumference or distance around the circle. So students often mix up pi r squared and 2 pi r. They look a lot alike, and that's why. But remember, if it's an area that's length squared, it must be r squared. Only the r will be the distance, which is the circumference. One additional shape I ask students to get to know generally is the equilateral triangle. There is not a perpendicular base or height. How do we calculate the area of this shape? Because we see it quite often. One way to think of it is as 2 30, 60, 90 right triangles. Every interior angle is 60 degrees on my equilateral triangle. And if I split the one up top here into 2 30-degree angles, I know I bisect the opposite side, and let's call this side S for my equilateral triangle. That means I'm going to down here have 1/2 S and 1/2 S. Now I have a height that's perpendicular to my base, and I can use that to derive my area formula. See how useful the 30, 60, 90 right triangle is? You definitely want to get to know and memorize that. How would I go about this? Well, I know the height, if this side on the base here is 1/2 s, the altitude here will be √3 times that, or √3 s divided by 2. That is my height. Now I can calculate the area. The area of any triangle is 1/2 base times the perpendicular height. In this case, that's 1/2. My base is s, if I consider the entire base, times my height, which is √3s over 2. Let's multiply that out. I get √3s squared over 4. If I multiply that out, 1/2 s times √3s over 2, I will get s squared √3 divided by 4. The area of an equilateral triangle of side S is √3 over 4 times s squared. That's one I would commit to memory, or know how to quickly derive it knowing your 30, 60, 90 triangle, which I hope you commit to memory as well. And this is actually useful if we have a regular hexagon, because if you notice regular hexagon, poorly draw in here, breaks into 6 different equilateral triangles. So what would the area of a regular hexagon of side SB? It would literally just be 6 times my area above. Root 3 over 4 s squared. That would be the area of my regular hexagon. Let's look at a couple examples of calculating area. For example, I've got a rectangle with a width of 6 and an area of 60 square units. Suppose I want to find the missing length right there. How would I go about doing that? Well, I might realize 60 square units, I've got 10 units in length. And what I do know is the hypotenuse of this right triangle, effectively the diagonal of my rectangle, is going to adhere to Pythagorean theorem. So I know that distance is going to be the square root of 6 squared plus 10 squared, which is the square root of 136. Okay, that's fine. I know this triangle represents half the area, so it's essentially 30 square units. I have the base, and the missing length is my height. So I can say 30 equals 1/2 square root of 136 times my missing amount, whatever that turns out to be, and go ahead and solve for that. Let's look at the next case. Area of a triangle, I see 2 triangles, A and B. The area of A is 10. Well, some students, and the question here is, what's the area of B? Some students might try to do 2 times 12 times 1/2. 1/2 your base times height. That's not correct, because again, 12 is not your perpendicular height. Your perpendicular height is right there. And we essentially don't know that particularly offhand, unless we take advantage of the fact we know the area of A, because we know that area must also equal 1/2 base times the perpendicular height. Our base there is 2. So 1/2 times 2 is 1, which means our height must equal 10 in this case. And then I could use that to calculate the area for B. The area for B will be 1/2 the base, 3, times my perpendicular height, 10. The area of B is going to be 15. Another thing to note is whenever you have the same heights of triangles, the ratio of the areas will be the ratio of the bases. 3 to 2 is the same ratio as 15 to 10. I really didn't even need to find the height as an intermediate answer. Next, I've got 3 triangles embedded in a rectangle, A, B, and C. My rectangle is 6 by 10. I want to know what is the area of A plus B. How would I go about figuring that out? I don't have any other data. These lines don't provide any detailed information. Well, what do I know? I know the height of each triangle, A, B, and C, is always equivalent to 6. And the base of A, I don't know that. That's part of the problem. And the base of B by itself, I don't know that. But together, they are the full length of the rectangle. So I don't know individually what A is, and I don't know individually what B is, but combined, they must be 1/2 my rectangle area. They're going to be 1/2 the combined base, which is 10, my length of my rectangle, and the perpendicular height of each of those triangles is the width of my rectangle, 6. A plus B must be 30 square units. One rudimentary skill for circles is to be able to connect circumference to area. Circumference is 2 pi r. Area is pi r squared. They connect through the length of the radius. So, for example, if I was given a circumference of a circle of 8 pi, I could calculate my radius. That 2 pi r must equal 8 pi. Solving for r, the radius is 4. Once I know my radius is 4, I can go ahead and calculate my area, which is pi times the radius squared, or 4 squared, which is 16 pi square units. Be careful. Areas are square units, very different than circumference or lengths, which are scalar units. Another typical application you want to understand in word problems, etc., is how a circle or a wheel would roll. For example, let's take my circle or wheel of radius 4, and if I rolled it 100 revolutions, how far would I travel? How many units of distance? Each revolution is 1 circumference in length around the circle, which means I multiply the number of revolutions times my circumference of 8 pi, which gives me a total distance, assuming there's no skidding on my wheel or tire, that's equal to 800 pi units. Or alternatively, I might have a total distance, be given a radius of a wheel, and have to calculate how many revolutions that wheel would make. So again, you want to know and get comfortable with that concept. It appears on various types of word problems. The test will almost certainly test your ability to scale not just distances, but areas and volumes as well. So assume we have a circle of radius 4 here again, and I double my radius. What happens to the circumference? Well, my circumference is 2 pi r. Notice my function is directly related to r. So if I double r, I would plug in 2r for my new radius, and my function value will be 4 pi r, which is twice the circumference before. So circumference is a direct relation to r. If I double r, I double my circumference. I have r, I have my circumference. How about area? What happens when I double my radius? The area is pi r squared. It's proportional to the square of the radius. So if I double my radius, in this case, I would plug in 2r for r, which in turn is 4 pi r squared. R squared was our original area, so this is really 4 times my original area. Notice my area factor quadrupled. It did not just double when I doubled my radius. Why is that? Area factors in general equal the scale factors squared. So if I double my scalar lengths, I quadruple my area. If I increase my scalar lengths by 50%, or a factor of 1.5, 100% plus 50%, I would square that to get the new area, which would be 2.25, or an increase of 125% in area for a plus 50% increase in the lengths. And again, it doesn't matter if this is a circle, a triangle, a square, or any two-dimensional shape. The relationship between the area factor and the scale factor squared can be very helpful to know for the exam. In many cases, the objects being scaled will be three-dimensional shapes. And right away, you're probably wondering, oh, I have to remember three-dimensional volume formulas as well. Well, let's start off. I'm going to share a little tip. There are only 2 things you know to remember pretty much every volume formula for all the prisms, and most of the shapes will be prisms. What is a prism? A prism is a base, like a circle or a triangle or a rectangle, extruded through a width or a height, which means the volume of any prism equals the area of the base times the height or the depth. So that's the height, that's the height, that's the height. The area of the bases are the shapes we already know. A circle for a cylinder. So in this case, a cylinder volume would be pi r squared h. For a triangle, the area of the base would be the triangle. The volume of the prism in that case would be 1/2 base times height times the height. Not to confuse this height, let's call this height the height of the triangle. That is the altitude. Not to confuse that with the height or depth of the prism itself. In a rectangle, the area of the base is length times width. Length times width times my height. We don't need to remember all three formulas, or for any other shapes, the different formulas. It's simply the area of the base times the height. Okay, that's well and good. That's the first part. The second part is if I take any of these shapes up to a point, like for a cone, I make my cylinder a cone that fits just inside, or my triangular prism to a triangular pyramid, or my rectangular prism up to a point, a rectangular pyramid. It's true that the volumes of each of these cones and pyramids equals 1/3 the volume of your prism. It's that simple. If I have a cylinder of 30 liters, the cone that fits right inside would hold a volume of 10 liters. Let's see a typical example where the scale factors are at work on a three-dimensional shape. Perhaps we have a cylinder, and they tell us we double the radius and halve the height. What's the ratio of the new volume to old? They don't even give us any numbers or dimensions for that cylinder. What do we know? We know the volume of a cylinder is going to equal the area of the base, which is a circle, so it's pi r squared, times the height, or the depth of that cylinder. Okay, so what are they telling us? They're doubling the radius. That means everywhere where I see r, I want to insert or substitute 2r. So pi, for my volume formula, times 2r, rather than r, I substitute, squared times my height. And instead of my height, the variable h, I'm halving that height. So I want to substitute h over 2 in this case. Now I can see exactly what my new expression evaluates to. This is going to be pi times 4r squared times h divided by 2, or if we wrap it up together, it's essentially going to be 2 pi r squared h. Well, guess what? Pi r squared h, that was my original volume. So the ratio of the new volume to the old is going to be 2:1, and that's the answer to the question. Now, again, if we're used to understanding how our variables are affected, how an area factor is essentially a scale factor squared, then we can actually see the components conceptually at work here. The radius is squared. So if I double my radius, I quadruple my volume, all else equal. The height is directly proportional to the volume. So if I have the height, all else equal, I have the volume. So I'm essentially multiplying my volume by 4 for the radius expansion and 1/2 for the contraction in the height, which is a net change or net ratio of 2 times. Exactly the answer we got from using the formulas. The other volume, a shape you should know, is the sphere. I could give you a couple tips and tricks there, but the truth is it's just as quick or even quicker to memorize. The volume of a sphere is 4/3 pi r cubed, and the surface area of the sphere is 4 pi r squared. If I looked at a similar scaling problem, the radius doubles for my sphere, what happens to the new volume? The volume new to the volume old will equal my scale factor cubed for volumes. In this case, that's going to be 2 cubed. The volume will be 8 times. Volume new to volume old will become 8 times from doubling the radius of my sphere. The surface area, as all areas, are squared factors. The surface area would quadruple given a doubling of the radius or the scale factors. Let's start off triangle theorems with the Pythagorean theorem. No, I think we know the Pythagorean theorem. A squared plus b squared equals c squared for a right triangle. Know your special triples. 3, 4, 5, 5, 12, 13. No, we're going to start off with the triangle inequality theorem. This basically assesses what range of side lengths make my triangle possible. So if I have a couple side lengths given to me, what third side length will close a triangle? Well, the first thing we note is A, the side shown here must be less than the sum of the sides B and C. If we see from the diagram, it looks like A is longer than B and C. That's a problem. That inequality, number one, won't work out. Well, that also means your triangle will not close. It needs to close. So A must be less than the sum of the other two sides, B and C. And that's basically your triangle inequality. Each side of a triangle is less than the sum of the other two sides. So we don't have just one inequality for side A. That's also true for side B. B must be less than the sum of C and A, the other two sides. C must be less than the sum of A and B. So I can put together three inequalities and solve for the missing sides that would work for my triangle, given some sides already in the problem. We can take a step further and do the additional work in blue here to boil down the last two inequalities, recast them in terms of A. A is greater than B minus C, and A is greater than C minus B. Notice those are the same magnitude or values, but one is going to be positive and one is going to be negative, because B minus C is the opposite of C minus B. Well, that means one's negative, but guess what? We already know the side lengths, whether it be B or C or A, they're all greater than 0. So one of them is not a useful condition for us. We can essentially boil this down to a second condition as opposed to 3. A is greater than the absolute value difference or positive difference between B and C. So let's see this all in action in a particular problem. Suppose I had a side length 10 for B and let's say a side length 5 for C. For what range of values for A would my triangle exist according to this inequality theorem? Well, first I would say condition 1, A is less than B plus C, which is to say A is less than 10 plus 5. A is less than 15. Okay, that's one condition. That's a useful constraint. How about my second condition? A is going to be greater than the positive difference. Well, I know B minus C is the positive difference there. So it's greater than 10 minus 5. A is greater than 5. I have conditions that's more constraining than saying length is greater than 0. My result would be A is less than 15 and greater than 5. If that's the case, my triangle will close and it can exist. If A were less than 5, say 2, my triangle can't exist. What would happen? 10 would be too long for 5 and 2. A and C sides would not close. If A were 20, greater than 15, for example, well, then the sides B and C, as shown in this diagram, won't close. The net result is A is between 5 and 15. And that's what our triangle inequality theorem does. It allows us to find ranges of side lengths that make triangles possible. That is, the ability to actually close the three sides. What are similar triangles? Well, they're triangles that basically look alike, that have the same shape. And that's actually a pretty good notion, because triangles, they all seem to have the same shape. Triangles that don't have this shape, for example, may be a right triangle. That does not look similar to any of those. In fact, it probably looks more like a shoe of some sorts than a triangle. An obtuse triangle, that looks very different than the triangles shown. These are not similar triangles to the ones shown above, because they don't look alike. Well, what does that mean mathematically? It means they don't have the same interior angles. If this one has a right angle for a right triangle, the others don't seem to have right angles. Similar triangles must have the same interior angles. That's what gives them the same basic shape, regardless of how big they are. And then the question is, well, how big are they? They must be proportional in scale. So every corresponding side of a similar triangle must be scaled by that same proportion, that same scale factor. And that goes hand in hand with having the same interior angles and shapes. Last but not least, even if we rotate, say, this triangle around, and it goes upside down like this triangle here, they are still similar. If they have the same interior angles and proportional sides, they maintain similarity regardless of rotation or reflection. We now know what a similar triangle is. How do we find similar triangles or identify it? We have a handful of basic methods to identify similar triangles. The first is angle-angle, or AA. If I know two triangles have the same angles, say 50 degrees and 70 degrees, and maybe over here I have 70 degrees and I have 50 degrees. I've identified two angles that are the same between the two triangles. Therefore, they must be similar triangles, denoted by that squiggly mark. Well, okay, how do I know that? Well, the third angle must always be the same as well. Remember, the sum of interior angles of any triangle sums to 180. So if I have 50, 70, the remaining angle must be 60. And sure enough, the remaining angle, if I have 50, 70, must be 60 here. Therefore, if I just have two of the angles, I know all three meet my condition, same interior angles. So AA is probably the most common method you're going to see to prove similarity of triangles. Number two, side angle side. What exactly would that be? Well, okay, that means maybe I have a side length of 1 and a side length of 2 here. And who knows, maybe it's a 60 degrees in between. Okay. Over on this triangle, maybe I have a side length of 4 and a side length of 2. This would meet side angle side methodology. The scale factor from 4 to 2 on the other side of my 60 degree angle is also 2 to 1. The angle in between the 60 degrees is the same. So I have side, angle, side in the same ratios with the same angle in between. Those two triangles would therefore be similar based on side, angle, side. Sorry, that's not really my similarity symbol. Trying to draw vertically, it just looks like an S. My apologies. The next method is side, side, side. If I had side lengths 3, 4, and 5 on one triangle, and ignore the angles for you students of trig, you probably point out, no, those degree measures don't correspond to a 3, 4, 5. You're correct. I'm just trying to make a point. If I had 3, 4, 5, and over here I had, say, 10, 8, and 6, I would have 3 sides, and they're all scaled by a proportion of 2 to 1. 10 is twice 5, 6 is twice 3, 8 is twice 4. These triangles must be similar. By the way, notice these are rotated, but that still doesn't matter. They have proportional sides. They meet our SSS condition of similarity. Our last but not least one is right hypotenuse side. So if I do have a right triangle and I have the hypotenuse and any one of the sides, I know they must be similar triangles, assuming their proportions. So be careful. There are a few possible methods that students could try but do not work. The first one is ASS. If you're using this to put similarity together, angle, side, side, well, just look what it spells. I think it's kind of obvious that doesn't work. Anything that's an angle, side, angle, that doesn't work for similarity either. Most similar triangle problems end up in proportions. They're used to identify missing side lengths from the proportions we can set up knowing they're similar triangles. So we know what similar triangles are. We know how to identify them. Where students often make mistakes and get caught up is by incorrectly applying the corresponding proportions for the similar triangles. So how do we do that? In many cases, we might just look at, say, left side to left side, base to base, right side to right side. And we get the proportions A to X should equal B to Z equals C to Y. And then I can set up consistently from there exactly what I know and fill out the information I need to find. Okay, that's well and good if it works out that way, but what about the triangle here on the right? It's flipped or rotated. It looks upside down. What is my base? What is my left side? What is my right side? Remember, we can flip, rotate triangles and still maintain similarity. So what is the right proportion? Is it still A to X, B to Z, C to Y? The simple answer is no, not necessarily. So we need some accurate, reliable methods to correctly set up the proportion equations. That is the key to similar triangles. So what are those methods? Well, let's look at them from simplest to hardest. If we're given side, 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 all three side lengths, well, great. Not only can we identify similarity, we can actually see what's the smallest side, the middle side, and the longest side, and match small to small, middle to middle, long to long. Great. Easy to set up proportion equations there, relatively. Number two, if I'm given a similarity statement like triangle ABC is similar to triangle XYZ, they just told me what sides are corresponding. A vertex corresponds to X. The middle corresponds to the middle, and the end corresponds to the end, which means side AB is proportional to the first two, X, Y. And then I could also say side BC, the last two, is proportional to the last two, Y, Z. And I could also then say AC, the first to the third, is proportional to XZ, the first to the third. In other words, I have a definitive setup of proportions I can work because I basically work in the same order when given the triangle inequality statement. So great, if they give me that, I'm also in good shape. The problem comes with what if the triangles are not aligned like this? There's clearly some kind of rotation or some change going on, and I need to identify the right proportions. What do I do? The correct answer is you use your interior angles. Remember our geometry theorem? There's a relationship between interior angles and the opposite side lengths that allow us to effectively order small, middle, and long opposite sides, but from our interior angles. So for example, suppose I knew the angles in my original ABC were, let's say 50, 60, and 70. And I knew the angles in this triangle were 70, 60, and 50. We knew from AA that these triangles were similar, for example. Well, how do I set up my proportion equations? The side opposite 50 here, C, will be proportional to or correspond to the side opposite 50 here, which is X. The side opposite 60, B, will correspond to the side opposite 60 in the other triangle, Y. The side opposite 70, my longest side, A, will correspond to this side opposite 70, the longest side of the other triangle, Z. So I've used my interior angles to set up small to small, middle to middle, large to large, a correct proportion equation. This is where students make a lot of mistakes, but if you learn how to do this correctly, you'll be in excellent shape. You may find you also need to know the tests for congruency, not just similarity. Well, the similarity test, there are a few of those. How do I not mix those up with the congruency test? There are A's, S's flying back and forth. There's a simple way to remember it. If I know my similarity methods, SSS, SAS, and RHS are all tests for congruency as well. So I can remember the same basic tests work for similarity and congruency. The one that does not work is AA. I cannot port over AA to congruency. Why? Let's think about that. If I have a triangle here, it has the same angles as the triangle here. They are not congruent, which means they must be the same lengths, not just proportional or have a scale factor of 1 as their proportionality. These are similar, not congruent triangles. So AA is not sufficient to denote the correct same sizes. But if we remember ASA, which didn't work in similarity, I can basically use any double angle with a side to work for congruency. So ASA, AAS will be good tests for congruency as well. Well, okay, what about our last one that didn't work? Well, guess what? If you try to use that word for congruency again, like similarity, well, you're just, it doesn't work. Let's discuss complex numbers. They arise from time to time in exam for roots of quadratics and polynomials. We will also run into problems asking us to manipulate complex numbers. What are complex numbers? Well, we learned about real numbers. That's anything you put on a number line. Integers, rational numbers, evens, odds, primes. That was different than imaginary numbers, which produced a negative when you square it, so it could not be put on a number line. We defined it as imaginary, a separate set. What are complex numbers? Complex numbers are the superset of real and imaginary numbers of the form a plus or minus bi, where a and b are constants and I is the imaginary number. I can state any real or any imaginary number as a superset complex number of this form a plus or minus bi. For example, the number 5, you might say, well, there's no imaginary component to that. That's not a complex number. Oh, yes, it is. It's 5 plus 0i. Okay, what about 3i? Well, that's just a pure imaginary. Is it? It's 0 plus 3i. Note, I can express any real or any imaginary number as a complex number. Just like fractions or polynomials, you should be able to add, subtract, multiply, and divide complex numbers. How do we do that? How do we add and subtract complex numbers? Suppose I had 2 plus 3i minus 2 times 1 plus I. What would that be? Well, again, I'm going to distribute. There's a 1 there not shown. 1 times 2 is 2. 1 times 3i is plus 3i. Minus 2 distributing to the 1 is minus 2. Minus 2 distributing to the I becomes minus 2i. Now I can combine like terms. My I terms are unlike my constants, but I can combine them each individually. 2 minus 2 cancels out. 3i minus 2i becomes 1i or I. That's the answer to how I add or subtract. Simply speaking, I distribute, I treat them just like we would another variable. There's nothing unusual about adding or subtracting complex numbers. How do I multiply complex numbers? Suppose I had 2 minus I times 3i plus 5. How would I multiply that out? Well, the same way we would FOIL. I might do 2 times 3i for 6i. 2 times 5 is plus 5. Minus I times 3i is minus 3i squared. Minus I times 5 is minus 5i. Now I'm going to combine like terms. But before I combine like terms, I'm going to note something a little special here. I squared. I squared is a separate term. It's actually a real number. Remember, the definition of I is the square root of negative 1. So I squared is simply negative 1. So I'm going to substitute negative 1 for my I squared. And now I'm going to combine like terms. 6i minus 5i is 1i. 5 minus 3 times minus 1 is 5 plus 3. This becomes 8 plus I. Again, multiplying is very much the same as we would with any other variables in algebra. We would FOIL it much the same way. We distribute much the same way. We combine like terms much the same way. The only catch for many problems is to remember that I squared can be reduced to negative 1, which might help simplify things. How do we divide imaginary numbers? What if I had 5 divided by I? Well, remember, I is the square root of negative 1. So this is basically the equivalent of 5 divided by the square root of negative 1. And we already know we need to rationalize the radicals. We can't leave the square root symbol, the radical, in the denominator there. So how do we get rid of that? Well, one way to do that is to multiply by I over I. Essentially, we're still multiplying by 1, so I'm not changing the value of my original expression. But I'm recasting it now to 5 times I is 5i in the numerator, and I times I is I squared in the denominator, and we know that I squared becomes negative 1. So this becomes negative 5i. We got rid of the denominator, we got rid of the radical, and our answer for this division is minus 5i. But what if I were presented with something like 2 over 1 plus I? I can't simply multiply by I because my I is going to multiply by that 1 in the denominator, and I'm still going to have an I in the denominator term, which means I still have a radical and I haven't rationalized this. So what can I do? Well, we're going to do something that we saw with our square roots and rationalizing similar binomial situations in the denominator. We're going to multiply by the conjugate, top and bottom. So 1 minus I on top over 1 minus I on the bottom is again essentially multiplying by 1. It doesn't change the value of my original expression, but it is going to recast our division problem. Multiply out the numerator. 2 times 1 is 2. 2 times minus I is minus 2I in the numerator. And the denominator is a product of the conjugates, essentially a difference of two squares. I'll square the first, 1, and subtract the square of the second, I squared. But again, I know what I squared is. I squared is negative 1. So this really becomes 1 minus minus 1, or 1 plus 1 in the denominator. That's 2. So this is 2 minus 2I divided by 2. Now I can factor out my 2. 1 minus I over 2. Those cancel. The whole thing simplifies to 1 minus I. I have no i's, no radicals in the denominator, and I've rationalized my imaginary complex number. Let's look a little more closely at our pure imaginary numbers. As we said, I is the square root of negative 1 by definition, and we just investigated that I squared is the square root of negative 1 times the square root of negative 1, or negative 1. It's a real number. Likewise, I cubed would simply be negative I. We can think of it as I squared times I, where I squared is negative 1, so that just becomes negative I. I to the fourth, well, that would be effectively I squared times I squared, and we know that's negative 1 times negative 1, which is positive 1. And then we go I to the fifth. Well, what exactly is that? That's positive 1 for I to the fourth times I, which essentially is just I. And then I to the sixth is negative 1, and I to the seventh is negative I, and I to the eighth is plus 1. So two things you might notice going on here. Number one, every even exponent is a real number alternating between plus 1 and minus 1. So if I have any even exponents, I know I have a real number. If I have an odd exponent of I to the first, I cubed, I fifth, I seventh, I'm looking at imaginary numbers that alternates between plus I and minus I. That's fact number one. Number two, notice the cycle of values for I is a pattern that repeats every 4 exponents. After I to the fourth, I return to the beginning, back to the equivalent of I to the 1. And this whole process begins again at I to the 9th, at I to the 13th, every 4 exponents. So what if I had I to the 17th? What does that equal? Well, all I need to do for that is 17 divided by 4 is 4 remainder 1. All I care about is the remainder. That means this is going to be I. All right, that's fine. What about, let's say, I to the 35th power? What would that be? Well, 35 divided by 4 is going to be 8 remainder 3. I to the 35 is the same thing as I to the third. What about I to the 20th? Well, 20 divided by 4 is 5. And the remainder here is 0. What exactly does that mean? Well, that means I'm essentially at my I to the fourth value, which is plus 1. So let's think about that as a check here. An odd exponent of I should be imaginary. It is. An odd exponent of I should be imaginary. It is. An even exponent of I should be a real number. It is. Notice that first pattern. Also, now we know at any power of I, we know how to boil it down to one of our 4 repeating pattern cases. I minus I, negative 1 or 1.